Hello everyone, welcome back to my channel. I love physics. We'll be continuing the lecture on optics. So I request you to go through earlier lectures. Till then, like, subscribe and comment below. Thank you. Hello students, welcome to today's physics lecture. In the last lecture, we have seen the relation between the focal length, object distance and the image distance, that is 1 upon f is equal to 1 upon u plus 1 upon v. Also we saw what do you mean by lateral magnification, that is nothing but the ratio of size of image to the size of object. Also there is an important formula only for the spherical mirrors which states that the focal length of the mirror, either it may be concave mirror or the convex mirror, is equal to half of the radius of curvature, and this formula is applicable only for the spherical mirrors. So we'll see the problems related to these formulae. The first problem is a thin pencil of length 20 cm is kept along the principal axis of a concave mirror of curvature 30 cm. Now here thin pencil of length 20 cm is kept. That means the object is a pencil and its size is given, that is the object size is 20 centimeters, and also the radius of curvature of the concave mirror is given as 30 centimeters. Further, nearest end of the pencil is 20 centimeter from the pole of mirror. What will be the size of image of the pencil? Now here we have to consider the sign conventions which we have learned in the previous lecture. And for concave mirror we know that the focal length is considered as negative, image distance is also negative, the object distance is also negative, whereas the image distance is positive. So here we calculate f from radius of curvature from the previous discussed formula, that is half of the radius of curvature with a negative sign. So f comes to be minus 15 centimeter. Now for the nearest end, we'll consider the object distance as u is equal to u1. As it is kept on the left side of the concave mirror, it is considered as negative, which is minus 20 centimeter. And let the distance be v1. Substituting in the above formula, we get v1 as 60 centimeters. As we obtain the image to the right side of the mirror, it is taken as positive. Now we have to find out the size of the image. Since the nearest end is at 20 centimeter and pencil itself is 20 centimeter, we'll add up the distance so that we get the farthest end where it can be placed, that is considered as u2, which is negative of 40 centimeter. For this we'll consider the image distance to be v2. Again we'll substitute in the above formula and we'll get v2 as minus 24 centimeter. Now we got the distance, image distance for the nearest end and for the farthest end. So we'll subtract the two and we'll get the final distance of the image, which comes to be 36 centimeters. Next problem is a car uses a convex mirror of curvature 1.2 meter as its rear view mirror. Okay, as I earlier said that the convex mirror is used in the vehicle's rear view mirror. Okay, so here it is given that it has a radius of curvature of 1.2 meters Now a minibus of cross section 2.2 meter into 2.2 meter is 6.6 meter away from the mirror. So here object distance is given as 6.6 meter and the dimensions of the bus are given as 2.2 into 2.2. We have to estimate the image size. So it is given r as 1.2, from which we will find out the focal length, which is 0.6 meter. The image distance is 6.6 meter. As it is towards the left side of the mirror, it is considered as negative. Now we find the image distance by the formula 1 upon f is equal to 1 upon u plus 1 upon v. By calculating, we get that the distance of the image is 0.18 meters. But what we have to estimate here is image size, not the image distance. So we'll use another formula which we saw of the lateral magnification, which is equal to m equal to v upon u, that is the image distance upon the object distance, which is also proportional to the size of the image upon size of the object. Now this is very important. The image distance upon the object distance is proportional to image size upon the size of the object. So using this relation, we will find out here h2 is the image object size, sorry, h1 is the object size, whereas h2 we have to find out. Here it is h1, it is h1, that is the obvious. We get h2 as 0.2 meters, which is the image size. So here we have used two formulae. One is the relation between f, u and v, and another one is the relation between the image distance, object distance, and the image size and the object size, which we get from the formula of lateral magnification. Okay, so next point is defects or aberration of images. Now the above formula which we have considered for the focal length, image distance and the object distance is valid only for ideal cases, that is, it is based upon the following assumptions: that objects and images are situated close to the principal axis. Obtaining must be close to the principal axis. Now this is not valid for every case. So the second assumption is that rays diverging from the objects are confined to a cone of very small angle, that is, now here divergence means in the right side the image is shown here, in which a beam coming from the from the left side is getting diverged at an angle theta. Here this theta is the angle of divergence. In the same case, when we consider the mirror or lenses or the diverging ones, where the ray of light gets diverged, so for that, if this angle is small, it is valid for the ideal case, and if this angle is large, then there arises some defects or aberrations. So in our cases which we considered in the earlier ones, there the angle theta was considered as small, that is angle of divergence was small. But when this angle of divergence gets larger, then the aberrations or the defects arise. Also the third assumption is there, that is, if there is parallel beam of rays, must be close to the principal axis. Now the rays of light which are coming from the objects must be close to the principal axis. But in reality these assumptions does not always hold good. So it results in distorted or defective images. The commonly occurring defects are spherical aberration, coma, astigmatism, curvature, and distortion. Here we will be discussing only spherical aberration. Now, what happens in the spherical aberration is that the focal point is, there occurs two focal points. We have seen the focal point is nothing but the point where all the rays converge or appear to converge. But when the rays are coming from far object, or if the rays of light are away from the principal axis, then those rays which are at the corner of the lens, these are called as the peripheral rays, whereas those rays which are close to the principal axis are called as paraxial rays. And what happens is, the rays which are close to the principal axis, that is the paraxial rays, converge at a focal point which is given by F, which is shown here at point 2, whereas the peripheral rays which are coming from distant object, or which are away from the principal axis, appear to converge at a point different than the ones at which the paraxial rays converge. So here the points shown by 1 and 2. So there are two focus which appears in case of the rays which are away from the principal axis and the rays which are close to the principal axis. This gives rise to a defect which is called as the spherical aberration, and the distance between the two focal points is called as longitudinal spherical aberration. Now this can be removed only if we consider, now this is applicable only for spherical mirrors or lenses. So this can be substituted by considering parabolic mirrors or lenses, which are also under the category of curved mirrors. So we'll discussing only spherical aberration is only in your text. Okay, so next point is refraction. Now we have seen reflection where the incident ray was reflected back in the same medium from where the incident ray was coming. Now what happens in refraction is, there are two media from which a ray of light is being passed, and the ray of light passes from one medium to another medium. It changes its path, and this phenomena is called as refraction of light. Now when the ray of light is incident on the interface between the two media, it gets bent either towards the normal or away from the normal. In the figure it is given, the normal is nothing but a perpendicular line drawn between the two media, and the ray which is coming from one medium is called as the incident ray, which makes an angle of incidence with the normal, whereas the ray after undergoing refraction in the other medium is called as the refracted ray, which forms an angle of refraction with the normal. The total angle of deviation gives the extent of up to which the incident ray changes its path. So that angle of deviation is nothing but the angle between the incident ray which is extended in another media, and the refracted ray. So refraction is nothing but deviation of light when it passes from one medium to another medium. Now if the medium 1 from which the ray is incident is rarer and the medium second is denser. What do we mean by denser medium and rarer medium is, if we consider for example medium 1 as air medium and medium 2 as water medium, water is more dense than air. That means the number of molecules in a volume is greater than those of air, because air is gas and water is a liquid, and liquid is denser than air. So when the ray travels from rarer medium to denser medium, it appears to be close to the normal. That means it bends its path close to the normal. If we consider this as the incident ray, and this is the rarer medium, and this is the denser medium, so it bends towards the normal. Whereas in the second case, if we consider this as the denser medium and this is the rarer medium, the ray of light appears to diverge away from the normal like this. Okay, so this is all about refraction. We will be seeing further some definitions. What do you mean by the absolute refractive index? It is nothing but the ratio of speed of light in vacuum to that of the speed of light in that medium. The refractive index is denoted by letter N or Greek letter mu, and absolute refractive index is given by C upon V. Second is the relative refractive index. Relative refractive index is nothing but the refractive index which tells the ability of one medium to refract with respect to another medium. So refractive index of medium 2 with respect to medium 1 is defined as ratio of speed of light V1 in medium 1 to its speed of light in medium 2. Thus it is denoted as 2 mu 1 is equal to N2 upon N1, which is equal to V1 upon V2. Also, another formula for refractive index is given as ratio of real depth upon apparent depth. Now, what do you mean by real depth and apparent depth? It is shown in the figure given in the right side. Watch carefully. When we look at an object in a water surface or any other medium, here we are considering you are looking up on the fish in water. Now in reality fish is at another position, whereas when you look at the fish it appears to be at another point. So this happens because of the phenomenon of refraction. So this total length where you see fish is the apparent depth, whereas in reality fish is somewhere else. So that depth is called as the real depth, and which appears to us is called as the apparent depth. So the ratio of the real depth and apparent depth also gives us the refractive index. Okay, so in the next lecture we will be considering some problems related to refraction. Till then, keep reading and watch all the videos of the lessons. Thank you.